Okay, in this set of videos I'm going to talk about differentiability and go over problems 81, 83, and 85, in which we determine whether a function is differentiable mathematically. And that's one thing that we're going to have to be able to do, just as we had to determine where a function was continuous mathematically. And I have a sentence over here. It says, functions are differentiable wherever their graphs are continuous, smooth, and do not have vertical tangent lines. The first idea in there is that a function must be continuous in order to be differentiable. Most functions are continuous everywhere except at certain points. And at those points where a function is not continuous, any type of discontinuity, then at that point a derivative does not exist, or the function is not differentiable. The second thing, graphs of functions must be smooth in order to be differentiable. There should be no sharp turns. There should be no jagged lines, etc. inside a function's graph. If there are, then the function will not be differentiable at those points. So for example, the absolute value function, y equals absolute value of x, it has a sharp turn at the origin, and at that particular point the function is not differentiable. And the function that we're working with in this case is an offshoot, or is a child of that parent family of the absolute value. And so you'll know just by looking at this particular function that it is the absolute value function shifted one unit to the right. And because of that, it is going to have a sharp turn at x equals 1, and so it will not be differentiable at x equals 1. We still need to see how to do that mathematically. So two things we've covered so far. The function must be continuous, and you can see that this absolute value function is continuous. Second of all, it has to be smooth. Even though this function is continuous for all x values, it has a sharp turn at x equals 1, and so it's not going to be differentiable there. Now the third aspect is that functions can not have vertical tangent lines. Well, obviously functions can have vertical tangent lines, but they won't be differentiable at those points. So you could very conceivably have a function that is continuous, is smooth, and yet has a vertical tangent line. And because a derivative is the slope of a tangent line, and the slope of a vertical line is undefined, then there is no derivative at a point where the function has a vertical tangent line. So these three things all must be true. The function must be continuous, must be smooth, and must also have no vertical tangent lines. And again, we could be talking at a point or on an interval, etc. So then that leads us to the statement that a function is differentiable at a point if we can find the slope of the tangent line at that point. So in order for a function to be differentiable at a given point, we have to be able to calculate, we have to be able to determine, to find the slope of the tangent line there, and that tells us that the derivative exists at that point. Now mathematically we're going to do this using the alternate form of the derivative. And that looks like this. The limit as x approaches a of f of x minus f of a over x minus a. But since this is a limit, you recall that a limit is only going to exist when the left side limit and the right side limit both exist and agree. So we see that a function is differentiable. For a function to be differentiable, it implies that the limit as x approaches a from the left of f of x minus f of a over x minus a equals the limit as x approaches a from the right of f of x minus a over x minus a. And when that is the case, then a derivative exists and the function is differentiable at that point. And we'll pick this up in the next video.